Hello everyone. So welcome to the first hour of the 3-hour series where we are going to talk about moving charges and magnetism. In this hour, I will focus on the force acting on a charged particle when it is moving in a region containing magnetic field. Do remember these words of mine. Whenever you are learning anything related to magnetism, you have to pay special attention to the direction of force, the direction of field. The direction plays a very important role when we are talking about magnetism. So without wasting time, let's start learning the first thing, which is the force on a charged particle in magnetic field. So force on a moving charge in the presence of magnetic field. Let's say we have a charge q and this charge q is moving with some velocity v. Now at the position of the charge, let's say we have a magnetic field. The magnetic field is also a vector quantity like electric field. The symbol used to represent the magnetic field is B and it's a vector, so many a time use the vector B. Now what will be the force acting on this charge which moves with a velocity v in the presence of magnetic field B? So the formula goes like the force vector equals to q into v cross b. Do not remember that F equals to q v b sine theta or something. But a force is a vector quantity, and I am again and again repeating that. In the chapter of magnetism, what matters the most is the direction. If you won't know the direction, there is no point of reading this whole chapter. So, better do remember that the force acting equals to charge times v cross b. Now, since you get the force from the cross product of velocity and magnetic field, you need to find the direction of force using the right hand thumb rule. What does the right hand thumb rule tells us? If you have got two vectors A and B inclined to each other at some angle theta, and let's say you need to find the direction of A cross B. So if you need to find the direction of A cross B, align the fingers of right hand in direction of A, then curl the fingers of right hand towards B. While doing so, in whichever direction your thumb point is the direction of A cross B. If you do it right now and try to find the direction of A cross B, it will be coming out of the screen towards you. Similarly, if you try to find the direction of B cross A, align the finger of right hand in direction of B, curl the fingers towards A. While doing so, your thumb will point into the screen. And that is the direction of B cross A. So just by looking at this formula, I can say multiple important things, and you should remember all these important things by heart. The first point, on a charge at rest, no magnetic force will act. Why? Because if the velocity of the charged particle becomes zero, then you will say that the magnitude of the force will be zero, right? So on a charge at rest, no magnetic force will act. So for the magnetic force to act on a charged particle, it must be moving. You can't have a magnetic force acting on a charged particle at rest. The second point, if velocity is parallel to magnetic field or velocity is anti-parallel to magnetic field, then the magnitude of force acting is zero. If they have given me that force vector equals to q into v cross b, I can write that the magnitude of force will be equals to q times the magnitude of v into magnitude of b into sine of the angle between the velocity vector and the magnetic field vector. If the velocity of the charged particle is in the direction of magnetic field, so if v and b are parallel, or if the velocity of the charged particle is in direction opposite to magnetic field, so the velocity and magnetic field are anti-parallel, then in both the cases the value of sine theta becomes 0. Sine 0 is 0, sine 180 is 0. Since in both the cases the value of sine theta becomes 0, you will say that in both the cases the magnetic force will be 0. So just by looking at this formula till now, I have said two things. The first thing, if the velocity of the charged particle is 0, if the charged particle is at rest, then the magnetic force acting on it will be 0. The second point which I have said is that if the velocity and magnetic field are parallel, or if the velocity and magnetic field are anti-parallel, then the magnitude of force acting on the charged particle will be 0. Okay. Now let's see the next point. The direction of magnetic force is perpendicular to both velocity as well as magnetic field. Once more, the direction of magnetic force is perpendicular to both velocity as well as magnetic field. If you have got two vectors, vector A and vector B, can I say that A cross B will be perpendicular to both vector A and vector B? Yes, sir. If you think of the direction of A cross B right now, align the finger of right hand in direction of A, curl the fingers towards B. While doing so, understand that the direction of A cross B is coming out of the screen. While the vector A and B both lie in the plane of the screen. So both the vector A and B are in the plane of screen and A cross B is coming out of the plane of the screen. So the angle between A cross B and A is 90, A cross B and B is 90, A cross B and A is 90, A cross B and B is 90. So do understand that since A cross B is perpendicular to both vector A and vector B, similarly here, the force which you are getting from cross product of velocity and magnetic field has to be perpendicular to both velocity as well as magnetic field. So the third point tells us from just this basic formula, I can tell these 3 points. The first point, if the velocity is 0, magnetic force is 0. If the velocity and magnetic field are parallel or anti-parallel, then the magnitude of magnetic force is 0. And the third point, which I have said just now, is if you get force from the cross product of velocity and magnetic field, then the direction of force must be perpendicular to both velocity of the charged particle as well as perpendicular to the direction of magnetic field. This is the third point. Now comes the fourth point, which is very important point. We know that the power delivered by a force equals to force dot velocity. Can I say with 100% guarantee that the magnetic force acting on a charged particle must be perpendicular to the velocity of the charged particle? Yes, sir. Why? Because, sir, you are getting force from the cross product of velocity and magnetic field, and if you are getting force from the cross product of velocity and magnetic field, the force must be perpendicular to both velocity as well as magnetic field. As the force is perpendicular to velocity, I know that the power delivered by the force has to be 0. Why? Because the power delivered is nothing but force dot velocity. Since force and velocity both are perpendicular, the angle between them is 90, and we know that A dot B is nothing but magnitude of A into magnitude of B into cos of the angle between them. Cos 90 becomes 0. So here you simply get 0. The power delivered by a magnetic force to the charged particle is 0. So as power delivered equals to force dot velocity, and force and velocity are perpendicular. That's why the power delivered by a magnetic force has to be 0. This is the fourth point. Now let's talk further about the important points which you can say just by looking at this simple formula. The next point is, if the power delivered by magnetic force is 0, if the power delivered by the magnetic force is 0, what is power? Sir, power is the rate of doing work. So if the power delivered by the magnetic force is 0, the magnetic force can't do the work on the charged particle. And if the magnetic force can't do the work on the charged particle, then it can't change the kinetic energy. So the next point, so no change in kinetic energy due to magnetic force. Why? Because, sir, magnetic force you get from Q into V cross B. Yes, sir. So magnetic force has to be perpendicular to velocity. Yes. Since magnetic force is perpendicular to velocity, the power delivered by magnetic force, which is given by F dot V, has to be 0. If the power delivered by the magnetic force is 0, it means that the magnetic force won't change the kinetic energy. If the magnetic force won't change the kinetic energy, it means that if a charged particle moves only under the influence of magnetic force, its kinetic energy will remain constant. If a charged particle moves only under the influence of magnetic force, its kinetic energy will remain constant. And when I say kinetic energy, it is half mv square. So for kinetic energy to remain constant, it means that the speed has to be constant. So the speed do not change due to magnetic force. Sir, a force is acting, yeah, and the force is given by Q into V cross B, yes. And then you said that the force acts perpendicular to velocity, yes. So the power delivered by the force is 0. So the change in kinetic energy produced by this force is 0. So the kinetic energy remains constant. So the speed of the particle remains constant. But force is acting and speed is constant. Have you ever seen any motion in which a force is acting but still the speed is constant. Have you ever seen any motion in which a force is acting but the speed is constant? Uniform circular motion. When a particle performs uniform circular motion, then we know that the speed remains constant. But so as to make the particle perform uniform circular motion, there always have to be a force towards center. Without a force towards the center, the particle won't perform uniform circular motion. Okay, sir. So when a particle performs uniform circular motion, its speed remains constant despite a force acting, because we have learned in work power energy, the work done by radial forces is zero. So now we will talk ahead, but all these points are important. I will like you to pause the video and go through them once more before moving ahead. As I said in the very beginning, the most important thing here is direction. So now let's focus on a drill where we will focus on the direction of the magnetic force. Beta, the drill goes like, we need to understand first the six direction: north, south, east, west, up, down. So think that towards me, towards the screen, you have got north. So from you to me, it's north. From me to you, it's south. This is up, this is down. To your right is east, and to your left is west. So visualize this. You are sitting looking at the screen. The direction towards me is north. The direction towards you is south. The direction towards your right is east. The direction towards your left is west. This is up and this is down. So now I am going to give you multiple cases and you need to determine the direction of force in each case. So I will give you the number of question, the charge, the direction of velocity, the direction of magnetic field, and you have to tell me the direction of force. So case 1, you have got a positive charge. This positive charge has got velocity towards north. It has got magnetic field towards east. What will be the direction of force? So do remember that force equals to Q into V cross P. So if Q is positive, direction of force is same as that of V cross P. If Q is negative, if the charge is negative, then the direction of force is anti-parallel, opposite to direction of V cross P. So first case, we need to find the direction of force acting on this charge which has got velocity towards north in a place where the magnetic field is towards east. So align the finger of your right hand in direction of velocity, that is towards north. Your fingers should point towards me. And then curl your fingers towards east. This is curling towards west. This is curling up. This is curling down. You need to curl towards east. And when you align the finger of your right hand towards me and curl it towards east to your right, then doing this process, your thumb points downward. Since the charge is positive, the direction of force will be same as the direction of V cross B, which is north cross east, which is nothing but down. Second case, now you have got a positive charge which has got velocity in upward direction in a place where the magnetic field is towards north. Anyways, earth create its own magnetic field towards north. So they might just give you a charged particle has got velocity in upward direction. What is the direction of magnetic force? So you need to understand that earth has got its own magnetic field towards north. So if they do not mention the direction of magnetic field in the question, do understand they might be talking about earth's magnetic field. So nevertheless, what will be the direction of magnetic force acting on it? So you will say, sir, the charge is positive. Yes. The velocity is upward. Yes. So I need to align the fingers of right hand in upward direction. This is curling towards west, curling towards south, curling towards east. I need to curl my finger towards north. And when I keep my fingers upward and curl them towards north, my thumb point towards west. Do it every time. So when your thumb point towards west and the charge is positive, so the direction of force will be same as V cross B. So you get west. Practice out each one with me. The third one. Now the charged particle is negative. The velocity is downward and magnetic field is north. In this case, we know that the direction of force will be opposite to the direction of V cross B. Why? Because the charged particle is negative. So first of all, let's find out the direction of V cross B. V, velocity, is in downward direction. So align the finger of right hand in downward direction. This is curling towards south, curling towards west, curling towards east, we need to curl it towards north. So align downward, curl it towards north. When you do it, you get east. But the charge particle involved is negative. So you will have to turn your thumb. So the correct answer will be west. So in this case, the answer will be west. The force will act towards west. Next case, the charge particle is negative. Velocity is towards north. Magnetic field is upward. What will be the direction of force? Okay, so charge particle is negative. So the direction of force will be opposite to the direction of V cross B. V cross B is north cross up, north cross up. So align the finger of right hand towards north. This is curling towards west, curling towards east, curling down. We have to curl towards upward. So north cross up, the thumb point towards east. But this is the direction of V cross B, east. But the charge particle involved is negative. So I will have to make it anti-parallel. So the answer will be west. Next case, you have got positive charge, velocity towards south and magnetic field towards east. So velocity towards south. So align the finger of right hand towards south and then curl the fingers towards east. So align towards south, point your finger towards south and then curl the finger towards east. When you do this, your thumb points up, and as the charge particle is positive, the answer will be up. Next case, the charge particle is positive, velocity is towards west and magnetic field is downward. So velocity is towards west, align the finger of right hand towards west, curl the fingers downward, your thumb point towards U, that is south. So the answer is south. Next, the charge particle is negative, the velocity is towards east and the magnetic field towards south. So the charge particle is negative, so I have to flip in the end. So velocity is towards east and the magnetic field towards south. So east cross south gives me down, but since the charge particle is negative, I will flip it and I will get upwards. Next, the charge particle is positive, the velocity is downward and magnetic field towards west. So the direction comes out to be towards north. So you need to practice all of them. If you haven't got anyone, have faith the answer given is right. Think over it again, and you will be able to master the direction. If you don't know the direction in magnetism, there is no point learning it. Stop the video right now. It will never be useful for your NEET examination. To crack your NEET examination, you have to be master both of direction as well as magnitude, and magnitude part is super easy. I will make sure that you will remember all the formulas, but you won't get direction without practicing it on your own. So it will take some time. Rewind the video a little bit and see it again if you haven't understood any particular part. So without wasting time, let's move on and understand the charge particle projected in transverse magnetic field. So what is the meaning of transverse magnetic field? The region in which the velocity of the charge particle and the magnetic field are perpendicular. Such a case is called transverse magnetic field. Now let's say we have got this inward magnetic field, uniform magnetic field, and this magnetic field has a magnetic field strength P. We have learned that if we have, let's say, positive charge having velocity towards right, what will be the direction of magnetic force on this charge at this particular instant? So sir, V, align the finger of right hand in direction of V, curl the fingers towards B, which is into the screen, V cross B, the force comes out to be upward. So at this particular instant, the direction of force on the charged particle is upward. At this particular instant, the direction of force on the charged particle is upward. And we know that this charged particle is going to do such a motion in which its speed will be constant. Speed is constant. Velocity is not constant. Speed is constant. Why, sir? We know that there is a magnetic force acting on the charge. Yes. Will the magnetic force produce an acceleration? Yes. If the charged particle will accelerate, its velocity will change. Velocity will change. Yes. Velocity will change. Speed won't change, because we have learned that the power delivered by the magnetic force is zero. So the change in kinetic energy produced by it is zero. So the speed of the charged particle remains constant. Speed remains constant. Force is acting. It will accelerate. Its velocity will change. So think of a motion in which the speed is constant but the velocity changes. And you know that that's a circular motion. Now, we know that when a particle performs circular motion, then the net force acting on it is towards the center, right? So since this particle performs uniform circular motion, the net force has to be towards the center and the force is up. It means that the center has to be somewhere here on this line. So this charge particle must be moving in a circle like this. Similarly, rather than having positive charge, if let's say we have a negative charge with the velocity v towards right, in which direction the magnetic force will act on this negative charge? So sir, v cross b, but it's negative. So you need to flip the direction of force. So the force at this instant will be somewhere downward. We know that this charged particle is going to perform uniform circular motion. Why? Sir, speed has to be constant, but velocity can't be constant. Why? Because sir, force is acting. The force will accelerate. When the force will accelerate, velocity will change. So speed is constant, velocity is not constant. It means that the direction of motion is continuously changing. So this will be nothing but uniform circular motion. So you will get the particle doing uniform circular motion like this. Do understand that at any instant, if you know the direction of velocity and force, you can tell which type of circular motion it has to be, because the net force is acting towards the center in case of uniform circular motion. Now the first thing we need to focus upon is how to find the radius of the circular motion. So do understand that in this case, the charge projected in perpendicular magnetic field, the magnetic force provides the required centripetal force. The magnetic force provides the required centripetal force. We have learned that the formula of magnetic force is F equals to Q into V cross P. Yes, sir. We are studying the case when the magnetic field is transverse. So magnetic field is perpendicular to velocity. Can I say that if F equals to Q into V cross P, then I can write the magnitude of force equals to Q into magnitude of velocity, which is speed, into magnitude of magnetic field into sine of the angle between them. So we can write F equals to QVB sine 90. Since we are doing the case of transverse magnetic field, the velocity and magnetic field are perpendicular. So the angle between them is 90 and sine 90 is 1. Now this force acting towards the center provides the required centripetal force. So we can say QVB sine 90, sine 90 is 1, equals to the net force acting towards the center equals to centripetal force. So this has to be equals to mv square by r. So you can simply say bachcho, QVB equals to mv square by r. Cancel out 1v with 1v. So what you get is the radius of the circular motion has to be mv by qb. So the radius of circular motion has to be mv by qb. When the charged particle is projected in a transverse magnetic field, when the magnetic field is perpendicular to the velocity. Now mug up this formula with me right now. Radius of circular motion of a charged particle in transverse magnetic field is given by mv by qb, 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 mv by qb. You need to remember the formula, yes. But you need to even understand when does this formula work. When the charged particle is projected in transverse magnetic field. This means that the direction of magnetic field should be perpendicular to the velocity. Then the radius of circular motion is mass of the charged particle times its velocity upon the charge on it times the magnetic field strength. So radius equals to mv by qb. Now there are multiple more ways to write the same result. So let's say we have got charged particle projected in perpendicular magnetic field or transverse magnetic field. So we know that this charged particle undergoes circular motion, and let's say this circle has a radius r. So we can write this radius as mv by qbs. What is mv? Sir, mass times velocity. What is mv? Momentum. So you can write the same formula as the radius can also be written as p by qb. Yes sir, in place of mv, momentum, you can write p. And we know that kinetic energy equals to half mv square. Yes sir. So if you forcefully multiply and divide with an m on the right hand side, can I write that kinetic energy equals to m square v square by 2m, which is p square by 2m, or can I write that the momentum is under root of 2m ke? Yes sir. So in place of momentum, you can even write under root of 2m ke. So the radius can also be written as under root of 2m ke by qb. Right. Now in place of kinetic energy, you can even write the kinetic energy acquired by a charged particle is nothing but the charge on the charged particle multiplied by the accelerating potential. Whenever we accelerate a charged particle in a lab, we accelerate it through a potential drop. Now when we accelerate a charged particle with a charge q through a potential drop delta v, The kinetic energy gained by the charged particle is q delta v. So in place of the kinetic energy of charged particle, you can even substitute q delta v. So you will get the radius to be under root of 2 mq delta v by qb. So there is so many ways to write the same thing, and you should be able to write all of them really quick. So remember that the radius can be written as mv by qb. In place of mv, you can write the magnitude of momentum by qb. In place of momentum, you can write under root of 2 mke by qb. In place of kinetic energy, you can write the charge times the accelerating potential by qb. So there are so many ways to write the same formula. Now, if in the question they give you kinetic energy, use this one. If in the question they give you the accelerating potential, use this one. And if they give you momentum, use this. If they give you mass and velocity independently, use this. So depending upon the need, you should be able to correlate better if you know how to convert the same formula. Now let's talk about the very important thing, which is time period. Sir, you have told us that if a charged particle is projected in transverse magnetic field, that is, the magnetic field is perpendicular to initial velocity, yes, then the charged particle performs circular motion. Okay. Sir, you have even told us that the radius of this circle will be given by mv upon qb. Yes. Now, how much time it will take for the charged particle to complete the circular motion? So we know that if the particle moves with a speed v in a circle of radius r, then the time taken to complete one circular motion will be nothing but 2 pi r by v. And we have marked up that the formula of radius is mv by qb. So in place of r, I can substitute mv by qb. So I get time period equals to 2 pi mv by qb divided by v. This v and v get cancelled. So what you get is 2 pi m by qb. Now you need to mark this up. The time period for circular motion in a transverse magnetic field, when the magnetic field is perpendicular to velocity, is given by 2 pi m by qb. Mark it up right now. Time period equals to 2 pi m by qb. Time period equals to 2 pi m by qb. Time period equals to 2 pi m by qb. Time period equals to 2 pi m by qb. Time period equals to 2 pi m by qb. Mark it up. So this is the time period of circular motion when a charged particle moves with a constant speed in a transverse magnetic field. Now comes the special point, and the special point is the time period of circular motion is independent of the speed of the charged particle. What? Yeah, the time period of circular motion is independent of the speed of the charged particle. Visualize it this way. If you have got transverse magnetic field, a perpendicular magnetic field, you project a charged particle with less speed, very small speed, then it will move in a circle of smaller radius and come back. If you project it with a larger speed, it moves in a circle of larger radius and come back. If you project it with even higher speed, then it will go in a circle of even higher radius and come back. But in all three cases, the time period will be same. No matter how fast you throw it or no matter how slowly you throw it, it will have the same time period. And on this simple concept that the time period is independent of speed of projection, we have got a beautiful device made called cyclotron, which is used to accelerate the charged particle. Cyclotron can be used to accelerate the charged particle on this basic argument that the time period of circular motion of a charged particle is independent of its speed. So greater the speed, yeah, greater the radius, yeah, but the faster it is moving, so you get the same time period. The time period of the charged particle moving in transverse magnetic field is independent of its speed. Now moving on to, let's say we have given a charged particle a speed v, and now this charged particle moves in a transverse magnetic field. We know that to complete the whole circle, the time taken will be 2 pi m by qb. How much time will be taken by this charged particle to go from, let's say, a position A to a position B such that the angle subtended is theta? So how much time will be taken to travel this length? So sir, to complete the entire circle, to turn by 2 pi angle, the time taken is 2 pi m by qb. To turn by 2 pi angle, the time taken is 2 pi m by qb. So as to turn by pi angle, half the circle, the time taken will be pi m by qb. So as to turn by theta angle, the time taken has to be theta m by qb. So easy. Or you can go from the basic. You will say that, let's say the particle goes from point A to point B. So it moves along an arc. So you will say that the time taken to cover an angle theta will be the length of the arc, which will be r theta upon the speed. Now, in place of r, you can substitute mv by qb. Remember the formula. So you will write mv by qb into theta by v. Again, cancel out v and v. So what you get is time taken to turn through an angle theta is theta m by qb. Simple thing. So the time taken to turn by an angle of 30 degree will be how much? So simple, 30 m by qb. Okay, don't do this. Beta, in the world of physics, whenever we substitute the angle theta, it has to be in radian. So if they give you the angle of 30 degree, don't substitute 30 degree, substitute pi by 6. So you will say the time taken for this charged particle to turn through an angle of 30 degree will be nothing but pi by 6 into m by qb. Okay, so do remember that here you must substitute the angle theta in radian, not in degree. Now beta, remember that once you know time period, you can even tell what is the angular velocity. Okay, we know that the angular velocity equals to the angle turn upon the time taken, or omega equals to 2 pi by t. So you can get, substituting the value of t as 2 pi m by qb. So you get 2 pi upon 2 pi m, and the qb moves from denominator to the numerator, and you can cancel out this 2 pi and 2 pi. So the angular velocity comes out to be qb by m. Sometimes useful in question. The next thing is frequency. Frequency is nothing but 1 upon time period, and you know that time period is 2 pi m by qb. So the frequency of the circular motion will be qb by 2 pi m. So easy. So you just need to remember the time period formula. You will be able to remember everything else easily. The argument is, to turn by 2 pi angle, the time taken is 2 pi m by qb. So as to turn by theta angle, the time taken has to be theta m by qb, given that theta is taken in radian. And once you know the time period, you can find the angular velocity using 2 pi by t, which is qb by m, and the frequency is reciprocal of the time period. So you should be able to remember all these things really quickly. So now let's understand different type of charged particles when projected in a magnetic field. Let's say you have got an inward magnetic field into the screen and you project a positive charge. Now, when you provide the positive charge with some velocity, it will experience a force. In which direction? To find the direction of force, do V cross B. The thumb points here. When the thumb points here, it means that the force will be in this direction. So the charged particle will deflect due to this force. The speed will remain constant, but its direction of motion will change. If we take a neutral charge, let's say neutron, and project it with some velocity, then this neutral charge will keep on moving in the straight line. Why? Because we know that the magnetic force acting is Q into V cross B. For a neutral charge, the charge is zero. Since the charge is zero, there will be no magnetic force acting on it. That's why this neutral charge will keep on moving in a straight line, as there is no magnetic force acting on it. But if you have a negative charge, for a negative charge, when you give some velocity, the direction of force will be V cross B in the direction opposite to it. Why? Because it is negative charge. So the force will be somewhere here. So the force at this instant will be here. And because of this magnetic force, the path will be a curved path. So they might just give you the path and give you the direction of field and ask you which type of charge it is. Here we are talking about multiple type of charges. They can be positive charges, negative charges, electron, proton, positron, alpha particle. In the NEET 2019, a question came, what is alpha particle? And many students did it wrong. Such a basic question. So that you don't do it wrong in future, let's first, for a little bit of time, talk about different type of charged particles. What is their charge? What is their mass? So here we will talk about the type of charged particle, what is their mass, and what is the charge on them. So the first basic particle we are going to talk about is electron. The mass of electron is 1 upon 1837 in some book you will find 1844, but do not worry, nearly 1800 times smaller than the mass of proton. And the mass of proton is nearly equal to the mass of neutron, which is equals to 1 AMU. So you will say that the mass of electron is 1 upon 1837 AMU, nearly 1800 times smaller than the mass of proton. And we know that the charge on electron is minus E, which is minus 1.6 into 10 raised to the power of minus 19 coulomb. Now let's talk about the next particle. Then we have got proton. The mass of proton is nearly equals to 1 AMU, and the charge on proton is plus E. Same magnitude as that of electron but positive. So plus 1.6 into 10 raised to the power of minus 19 coulomb. Then we have got our neutron. The mass of neutron is actually greater than the mass of proton, slightly greater. But the mass of neutron is nearly equal to mass of proton, and that can also be said to be 1 AMU. Do remember that neutron is slightly heavier than proton. So the mass of neutron is nearly 1 AMU, and the charge on neutron is 0. It's neutron, neutral, 0 charge. Next we have got deuteron. What is deuteron? Deuteron is deuterium nucleus. Deuterium nucleus. What is deuterium? The isotope of hydrogen, which has got one proton and one neutron in the nucleus, and one electron revolves around it. If you excite the electron so that it leaves the atom, what you are left with is the nucleus, and deuterium nucleus is called deuteron. So what is the mass of a deuteron? A deuteron is made up of one proton and one neutron, so it has got mass of 2 AMU. And the charge on deuteron is same as the charge on one proton, because one deuteron is nothing but one proton and one neutron. The neutron doesn't have any charge. The proton has got charge plus E, so the charge on deuteron is plus E. Here I would like to mention one important thing. Proton is nothing but hydrogen nucleus. Proton is nothing but hydrogen nucleus. If you think of the hydrogen atom, it has got no neutron. It has got one proton in the nucleus and one electron revolves around it. If you excite the electron to leave the nucleus, if you provide it with sufficient energy to leave the nucleus, then what you are left with is the hydrogen nucleus. And the hydrogen nucleus itself is the proton. So do remember that proton is nothing but hydrogen nucleus. Deuteron is nothing but deuterium nucleus. The next thing we need to talk about is alpha particle. Alpha particle is nothing but helium nucleus. When we think of the helium atom, in the nucleus we have got 2 proton and 2 neutron, and there are 2 electrons revolving around the nucleus. If you excite both the electrons, then what you are left with is only the nucleus of the helium. The nucleus of helium has got 2 proton and 2 neutron. The nucleus of the helium has got 2 proton and 2 neutron. So the total mass will be 4 AMU, 2 because of the 2 proton, 2 because of the 2 neutron. And the charge will be only because of the 2 proton, and the charge will be plus 2E. Here, the last thing we are going to talk about is positron. Positron is the true antiparticle of electron. A positron has got mass same as that of electron, 1 upon 1837 AMU, nearly 1800 times smaller than the mass of proton. But the positron has the same charge as that on a proton. The charge on positron is plus E, same as that on a proton. Remember that. So the positron has got mass same as that of electron and charge same as that of proton. Positron is the true antiparticle of electron. Every time they are created together, and every time they annihilate, they die together. So electron and positron are antiparticles of each other. Now the next thing we need to focus on is that electron has the highest specific charge, that is the charge to mass ratio. Sir, why do we need to talk about the charge to mass ratio? Understand that when projected in a magnetic field, the radius comes out to be mv by qb. Think of it as m by q times v by b. M by q depends upon the property of the charge. For different charges, you will get different mass to charge ratio. The particle which will have highest mass to charge ratio will have highest radius. Highest radius means that the curvature will be more. Lower radius means that curvature will be less, right? So the charged particle which has got more mass and less charge, that will have more radius. Neutron has got infinite radius, that's why it's a straight line, infinite radius. So charged particle which has got more charge to mass ratio will have lower radius, it will bend more, it will curve more. The greater the value of charge to mass ratio, the smaller will be the radius. The greater the value of charge to mass ratio, the smaller will be the radius and more the charged particle will curve. Do understand that the charge to mass ratio of deuteron you will write plus E upon 2mu is same as the charge to mass ratio of alpha particle plus 2E upon 4mu. So here you will write plus E upon 2mu, here you will write plus 2E upon 4mu, plus 2E upon 4mu is as good as plus E upon 2mu. So the charge to mass ratio of deuteron and alpha particle is same. The charge to mass ratio of deuteron and alpha particle is same. Keep this in mind. The next thing we need to talk about is what is 1 AMU. 1 AMU is nearly the mass of a proton, which is nearly equal to the mass of a neutron. And this value of 1 AMU is nothing but 1.6 into 10 raised to the power of minus 27 kg. So every time you need to substitute the mass of proton, substitute it as 1.6 into 10 raised to the power of minus 27 kg. Each time you need to substitute the mass of neutron, substitute it to be nearly same as 1.6 into 10 raised to the power of minus 27 kg. Second thing, what is the charge? What is E? So we say that E is nothing but 1.6 into 10 raised to the power of minus 19 coulomb. The next thing, what is the mass of electron? The mass of electron is nearly 1837 times smaller than the mass of proton. The value comes out to be 9.1 into 10 raised to the power of minus 31 kg. So this is something important. You must know all these things. Many a time when the question comes from the very basics, students do it wrong. Many students I know did this alpha particle thing wrong in the NEET 2019 paper. Now let's practice a question. The question goes like, there are two regions of space, region 1 and region 2. In the region 2, you can see there is an inward magnetic field going into the screen. And in region 1, there is no magnetic field. And a charged particle of mass m, charge q, is projected with a speed v. And this charged particle enters the magnetic field region perpendicular to the boundary. Once the charged particle enters the magnetic field region, the magnetic force starts acting on it. And because of this magnetic force, it will go into a circular path. So question is, how will be the path of this charged particle? Will it ever come out of this magnetic field region? If it comes out, then what is the change in velocity? If it comes out, then how much time does the charged particle spend in this magnetic field region? And what is the average acceleration? So your question is, determine first the time spent by the charged particle in the magnetic field region. Second, the change in velocity due to the magnetic field. Magnetic field do not change the speed, but it changes the velocity, the direction of motion changes. And the third part, what is the average acceleration produced by this magnetic field? So how to solve this particular question? It's easy if you will visualize once the charged particle enters, as soon as it enters, what is the direction of magnetic force? So as soon as the charged particle enters, yes, the velocity is towards right, the magnetic field is inward. So assuming the charged particle to be positive, the force will be upwards and the force will be along the radial direction. So the center has to be somewhere here. And then this charged particle will start doing circular motion and will start moving in a circle with the center somewhere here. So as the charged particle moves doing the circular motion, we know that after reaching this point, it will have a velocity towards left. And once it reaches this point, it will cross the magnetic field region and then will move straight. So question is, what is the time spent by the charged particle in the magnetic field? What is the change in velocity due to field? And what is the average acceleration? Let's answer each part and let's visualize the motion. So this is the magnetic field region. Here the charged particle, which has a charge q moving with velocity v, it will enter the magnetic field region. As soon as it enters, it will experience a force in upward direction. So the center of the circular motion has to be somewhere here. So it will start moving in a circular path, but will be only able to cover a semicircle. Now, Once it covers the semicircle, how much time it would have spent in the magnetic field region. So you will say, to cover an angle theta, we know that the time taken is theta m by qb, where theta is substituted in radian. So as to cover pi angle, the time taken has to be nothing but pi m by qb. So easy. Second part, the change in velocity due to the field. The magnetic field can't change the speed, but it can change the velocity. It's a force. The magnetic force must change the velocity because a force is acting, but it can't change the speed. So question is, what is the change in velocity? So you will say, sir, initially the velocity is v towards right. When it comes out, it has got velocity v towards left. So if I take the direction towards right as positive, I will say that the velocity initial is vi cap. The velocity final is minus vi cap. So the change in velocity equals to final velocity minus vi cap minus the initial velocity, which is plus vi cap. So I get minus 2 vi cap. So the change in velocity has a magnitude of 2v in the negative x. So the magnitude of change in velocity is 2v. So the velocity changes by an amount 2v. So you will say that the change in velocity is 2v towards left. Now how to find the average acceleration? Average acceleration is nothing but change in velocity upon time taken. So the change in velocity is 2v, the time taken is pi m by qb. So the average acceleration has to be change in velocity upon time taken, that will be 2v upon pi m by qb. That gives you 2v qb by pi m. This is an easy thing. Let's see one more example of nearly the same time to understand better. The question goes like here, now you have got three regions, region 1, region 2, region 3. In region 1, there is no magnetic field. In region 2, there is an inward magnetic field of field strength B. The region 2 has a thickness D, and then there is region 3 again where there is no magnetic field. A charged particle of mass m, charge q, moves with a velocity v. It enters here. As soon as it will enter, it will experience a magnetic force upward. So the center of its circular path has to be somewhere here. Now there can be two cases. If this d is sufficient enough, then it will cover its semicircular path and will come back into the region 1. But if this d is too small or the radius of circular motion is too large, then this charged particle will move in an arc and will leave somewhere here. So you need to solve the following things in this question. To determine first the deflection if the charged particle reaches region 3. So what will be the deflection in the velocity if the charged particle reaches region 3? Second part, the minimum value of d, the minimum value of the thickness of the region 2 for the charge to return to region 1. So you need to solve both the parts. Let's do them one by one. So you will say, solving for first part, assuming that this charged particle moves with such a high velocity that it has got such a large radius of circular motion, once it starts performing circular motion after reaching the region 2, it comes out in the region 3. And we need to find the deflection in the velocity, this angle theta. So let's say the charged particle enters, then it goes along an arc, it comes out in the region 3 such that its velocity makes some angle theta, and our mission is to find out this theta. How to find? This question is super duper easy. Now once the child look at this and they feel like how to solve this, it looks tough, but it is a very easy question. How? Let's see. Do little bit of construction. Let's say the center of this circular motion lies somewhere here. So on doing the construction, you will say that the velocity and the radial vector have to be perpendicular. Yes. So if this angle is theta, this angle has to be 90 minus theta. This charged particle moves along an arc of radius r, where we know that the radius will be nothing but mv by qb. Now how to find this theta? Quite easy. You will say that this length is d. Yes. If I look into this right angle triangle, I have just marked. In this right angle triangle, the hypotenuse has a length r here. This angle is 90 minus theta, and this base length is nothing but the thickness of the region 2. So you will say that the width of the region 2 is d. Now, can you tell me, kids, what is the relationship between r, d, and 90 minus theta? So you will say r cos 90 minus theta equals to d. And once you know that r cos 90 minus theta is d, that can also be written as r sin theta equals to d. So now game over. Once you know that r sin theta equals to d, sin theta equals to d by r. So one can write from here theta equals to sin inverse d by r, or in place of r, one can substitute mv by qb and write theta equals to sin inverse of d upon mv by qb. The qb moves from denominator of denominator to the numerator. So you get dqb by mv. So from here we can find out the value of theta. Now the second part of question, the minimum value of d for the charge to return to region 1. What has to be the minimum value of d for the charge to return to region 1? So for the charge to return, you can visualize that the path should be such that this radius of circular motion should be less than equal to d. So the radius of circular motion should be less than equal to d, or you can say that the thickness of the region 2 should be greater than equal to radius for the charged particle to come back to the region 1. So now we have done both the part, and I know that both the parts are not at all tough. You just need to know them to remember them. So let's move on and talk ahead. Now we will talk about the cases when the charged particle is projected at some angle with the magnetic field. Till now, all we have talked about, in every case, the velocity and the direction of magnetic field were perpendicular. But what if the velocity of the charged particle makes some angle with the magnetic field? So let's say we have got this charged particle which moves with a velocity v, such that the angle between the velocity vector and the magnetic field vector is theta. So you can see that the direction of velocity is not at all perpendicular to magnetic field. The velocity makes some angle with the direction of magnetic field. Now sir, what to do? Beta, again what you did in projectile motion, you break down it into two directions. Break down the velocity vector into two perpendicular components. One in direction of field, that will be v cos theta. One in direction perpendicular to field, which will be v sin theta. And now start visualizing about them one by one. First of all, just focus about v sin theta. Forget v cos theta, just focus on v sin theta and the magnetic field. So if a charged particle has got velocity upward v sin theta and the magnetic field towards right, so the direction of force will be here. So the charged particle will perform circular motion due to the velocity v sin theta, which is perpendicular to b. So the charged particle will perform circular motion due to the velocity v sin theta. We already know that if the velocity is perpendicular to magnetic field, the charged particle perform circular motion. So because of the velocity v sin theta, the charged particle will perform circular motion. Okay. Now forget about v sin theta and just focus on v cos theta. If you have a charged particle and you give it some velocity in the direction of magnetic field, then how will the motion look like? Sir, we know that when the velocity is parallel or anti-parallel to magnetic field, the magnetic force is going to be zero. So in this case, no magnetic force will act on the charged particle, and as no magnetic force will act on the charged particle, it will go in straight line. So visualize them one by one. Because of this v sin theta, it will do circular motion. Because of this v cos theta, it will go in a straight line. The overall motion has to be the combination of these two motions. What will the combination look like? So circular plus a straight line, and that combination looks like a helical path, just like the DNA structure, helical path. So because of v sin theta, the particle does circular motion. If there would have been only velocity perpendicular to magnetic field, it would have done circular motion. Because of v cos theta goes in a straight line, if there will be no v sin theta and there will be only a velocity of v cos theta, it will go in a straight line. But due to the combined motion, it goes along a helical path. Circular due to v sin theta and straight line due to v cos theta. So this is what the path of the charged particle will look like, a helical path. In this helical path, they will ask you two questions. First, what is the radius of this helical path? Second, what is the pitch? Pitch means the separation between 2 points on the helix, the pitch. So here they will ask you about what will be the radius of the helix and what will be the value of pitch, the separation between two consecutive turns. So first of all, how to find the radius? So you will say that this particle performs circular motion. The radius exists because of the circular part. And the circular motion is being done due to the velocity component perpendicular to the magnetic field. We know that for circular motion, the radius is mv by qb. Yes. Here, because of which velocity the particle is doing circular motion? Sir, because of v sine theta. So what is going to be the radius? It's so obvious. The radius is going to be nothing but mv sine theta by qb. In place of v, just substitute the velocity component perpendicular to magnetic field. Game over. So the radius of helix has to be mv sine theta by qb. Now you get this pitch due to the horizontal velocity, the velocity in direction of the magnetic field v cos theta. Now this pitch has to be nothing but the velocity along the direction of magnetic field multiplied by the time taken to complete one circle. The time taken to complete one circle will be nothing but 2 pi m by qb, the time period of circular motion, which is independent of the velocity. So you will say that the pitch will be nothing but the velocity along the magnetic field v cos theta multiplied by time taken to complete one circular motion, which is 2 pi m by qb. So the pitch comes out to be v cos theta into 2 pi m by qb. I just remember it this way. So if you remember both of them, you will be able to get answers based on this thing. Now let's talk about charge in electric plus magnetic field. What if we project the charge particle in a region of space where both electric as well as magnetic field is present? So you will say due to the electric field there will be a force QE. Force is a vector quantity. Due to the magnetic field there will be a force Q into V cross B. Since both the fields are present, both of them will apply force and the net force on the charge particle will be equals to QE plus Q into V cross B. I am a liar if I tell you that this is how we get the net force. There is something more to it, but that is out of our syllabus. So just remember that the net force is nothing but the electric force plus magnetic force. Now here, whenever question comes in competitive examination from this particular section, it comes from the condition of zero net force on the charge particle. And there is a beautiful reason behind it. I will tell you the reason at the end of this page, but you need to focus that whenever the question comes, it comes on zero net force. So for the net force on the charged particle to be zero, despite the presence of electric field and magnetic field, for the net force on the charged particle to be zero, E plus V cross B should be equals to zero. If I say that the electric field vector plus V cross B vector has to be equals to zero, I can rewrite it as E equals to minus of V cross B. We have learned from cross product that A cross B equals to minus times of B cross A. So I can write this minus V cross B also as B cross V. So for the net force acting on the charged particle moving in a region of space where electric and magnetic field both are present, the condition is that the electric field vector should be equal to the magnetic field vector's cross product with the velocity vector. So E equals to B cross V. From this particular correlation, we can say one thing. Since you are getting the electric field from the cross product of magnetic field and velocity vector, since you are getting the electric field from the cross product of magnetic field and velocity vector, the electric field vector must be perpendicular to both magnetic field as well as velocity. So the direction of electric field must be perpendicular to both magnetic field as well as velocity. Okay, so keep this thing in mind. So the electric field must be perpendicular to both magnetic field and velocity for the charged particle to move with zero acceleration, to move with a constant velocity, or for the charged particle to move in such a way that no net force acts on it. So E equals to B cross V. The electric field must be perpendicular to magnetic field and velocity. Now, electric field always have to be perpendicular to magnetic field and velocity if the charged particle moves with zero acceleration. The answer is yes. Question is, do the magnetic field and velocity always have to be perpendicular? No. But now I will talk about a special case. A special case that if the magnetic field and velocity are also perpendicular. So electric field is always perpendicular to B and V both. But if let's say magnetic field and velocity also are perpendicular, so now all three are mutually perpendicular, E, B and V. Now you will say that if B and V are perpendicular as well, then you know that the magnitude of B cross V, which will be nothing but B into V into sine 90, which will be BV. So we can find out the strength of electric field. So if magnetic field and velocity are perpendicular, then you can write that the strength of electric field equals to BV into sine 90, and sine 90 becomes 1. That gives you BV. Or you can rewrite it as the velocity of the charged particle has to be equal to the strength of electric field upon the strength of magnetic field. So if the charged particle moves in such a way that the velocity is perpendicular to both electric field and magnetic field, and the charged particle moves with a constant velocity, means not accelerating, means zero net force, then you will say that the velocity of the charged particle must be equals to E by V. Now why do question come from here in competitive examination? Because this is the case of light. This is the case of the EM waves. Whenever EM waves are traveling, the speed of light is equal to the ratio of the amplitude of electric field oscillation upon the amplitude of magnetic field oscillation. So C equals to E by V. The same formula you will learn in light, the same formula is used here. So remember that if the charged particle moves with such a velocity that the velocity is perpendicular to both magnetic field as well as electric field, and it moves with a constant velocity, then the velocity has to be equals to E by V. This is the case of light. There is more correlation with the case of light. When I will teach you EM wave in few hours later, I will say that the direction of propagation of light is same as the direction of E cross B. That thing works here as well. The direction of velocity of charged particle has to be same as the direction of E cross B. So remember that the direction of velocity should be same as that of E cross B. So for a charged particle to move with a constant velocity in a region of space where both electric and magnetic field is present, the velocity of the charged particle should be equals to E by V, and the direction of velocity should be same as that of E cross B. So you need to remember these two things, because these two things are the same as case of light. That's why they are important, and that's why they are asked in competitive examinations. Sir, I haven't understood this. It will become even more clearer once I discuss light, but this is important. So remember it right now. Speed has to be equals to E by V. The direction of velocity has to be same as E cross B. Use this when the charged particle moves with a constant velocity, no net force, in a region of space where both electric and magnetic field are present, and electric field, magnetic field and velocity vectors are mutually perpendicular. So let's see a question based on this. The question goes like, a proton is moving with a constant velocity in a region of space where the magnetic field is 4 Tesla towards east. So the magnetic field is 4 Tesla towards east, and the electric field is 8 Newton per Coulomb towards north. So we know that electric field is towards north. As seen by you, the electric field is towards me, towards the screen, and the magnetic field is towards east. Determine the magnitude and direction of velocity of the charged particle given that the electric field vector, the magnetic field vector and the velocity of the charged particle are mutually perpendicular. So now this is the question, which type of question will come in your competitive examination, and do understand this is the case of light. So it is easy to find. So you will say that the velocity has to be simply equals to E by V. The strength of electric field is 8, the strength of magnetic field is 4, and the units given are SI units. So I will simply plug in the data and I will get the speed to be equals to 8 by 4, that has to be 2 meter per second. And the direction of velocity has to be same as the direction of E cross B. So align the finger of your right hand in the direction of electric field. The electric field is given towards north. And then curl the fingers in the direction of magnetic field. The magnetic field is given towards east. When you do this, your thumb points downward. So the charged particle must move with a velocity of 2 meter per second downwards. So the velocity of charged particle has to be 8 by 4, that is 2 meter per second, and the direction is same as that of north cross east. North cross east gives you downward. So hence you will say that the velocity has to be 2 meter per second in downward direction. Now comes the important point. Notice that the answer is independent of both magnitude and nature of charge. I know we are mentioned in the question, this is plus 2 coulomb of charge, minus 2 coulomb of charge, 8 coulomb of charge, minus 16 coulomb of charge. I never mentioned how much charge. But still, independent of the nature and the magnitude of charge, you are going to get the same result, 2 meter per second down. So do understand that for a charged particle to move at a constant velocity in mutually perpendicular electric field and magnetic field, the speed of the charged particle has to be E by B and the direction of velocity has to be same as E cross B. So notice that the answer is independent of both magnitude and nature of the charge on the charged particle. So moving on, let's talk about something called velocity selector. It's a very easy device. Now, what does a velocity selector do? Sir, the name tells it selects a particular velocity. Now, let's say you have got many electrons in a container and you want a particular electron coming out of it, a particular electron which has got speed of 2 meter per second. Why? Because if the electron will have a particular speed, it will have a particular kinetic energy, and then you can bombard this electron having a particular kinetic energy on a metal plate or something to do the experiment, and you will know how much was the kinetic energy associated with this particular electron. So just by using electric field and magnetic field, we can create velocity selector. How? Let's say here you have got multiple charge particles and all these charged particles are moving with different speed. Some of them have high speed, some of them have low speed, some of them have got very less speed. The arrowhead represents their velocity. And these are placed in mutually perpendicular magnetic field and electric field, whose value we can easily set. We can increase or decrease the electric field, we can increase or decrease the magnetic field. Now, the charged particle which will go undeviated will be the one for which the velocity will be equals to E by B, because on that charged particle the electric and magnetic force will cancel out each other. So you will say for V equals to E by B, the charged particle will show no deflection. So that particular charged particle whose velocity will be equals to E by B, and you can set this velocity by changing the value of E and B. So the charged particle which has got velocity equals to E by B will go straight without any deflection. By the way, if you have got another charged particle for which speed is greater than E by B, beta speed is greater than E by B, think of it as V into B is greater than E. So Q into VB is greater than QE. If Q into VB is greater than QE, it means that the force magnetic is greater than the force electric. If let's say the charged particles we are talking about here are positive, so what will be the direction of electric force on them? So downward, because they are positive charges, they will have force in direction of field. What will be the direction of magnetic force? Sir? Q into V cross B, upward. If V is greater than E by B, then the magnetic force will be greater than electric force. So the upward force due to the magnetic field will be greater than the downward force due to the electric field, and hence the charged particle will go up. So the charged particle will deflect up. Similarly, if V is less than E by B, so then you will say VB is less than E, so QVB is less than QE, so the magnetic force is less than the electric force. So for such a particle which will have velocity less than E by B, you will say that the electric force will be more than the magnetic force, and electric force will be downward. The magnetic force V cross B will be upwards, and on such a particle the net force will be downward. It will deflect in the downward direction. So here you have got multiple particles. You can choose the value of E and B such that their ratio is equal to the velocity that you require. Now those particles with velocity equals to E by B will go undeflected. Those particles which have got velocity greater than E by B, they will deflect upwards. Those particles which have got velocity less than E by B, those will deflect downward, and only the particle which has got the same velocity as E by B will go straight. And that's how a velocity selector works. So that's all in this hour. See you guys in next hour, where we will talk about force on a current carrying wire and the magnetic field produced by a current carrying wire. See you guys in next hour. Bye bye. So that's all for now. See you guys in the next hour.